So today's webinar, AEC professionals are discovering better ways to deliver quality projects through model-based simulation, and owners are expecting that. Welcome to Simulation-Driven Design. Autodesk family of simulation products and software provides a comprehensive set of solutions to help you gain competitive advantage in solving the most challenging design problems. In this webinar, you will learn how to analyze and predict building performance, optimize and validate design options to ensure your design meets design constraints. Explore quality and safety requirements before construction begins. Utilize Autodesk family of simulation apps with proven technology and reliable accuracy to simulate building performance over time. Finally, integrate simulation results into your BIM authoring tool to help you make better design and business decisions. So that's in a nutshell what this seminar is about. Let's get started. So some of you may have heard of the 2030 Challenge. This is a program that was put together by a couple of organizations. One of them is AIA, and had challenged architects and AEC professionals to meet certain requirements for sustainable design by year 2030. In a nutshell, the chart on the left shows that today we stand about 70% fossil fuel energy reduction, and we're still using some fossil fuel and some renewable energy. That amount of energy reduction is going to increase over time, and then by year 2030, hopefully we can get to the carbon neutral level. We still need, as you can see, that there will be some renewable energy required by year 2030 to meet that challenge. The chart on the right shows how Autodesk was able to work with AIA and respond to those challenges. Autodesk now provides cloud services that can help you meet those design requirements. With these applications or cloud services, you'll be able to set a baseline and predict the energy performance of your building over time, and then set some goals and look at the savings, move in real time as you do modifying the design itself. And then of course you can upload that to AIA DDX to get to send a report over to AIA. So in 2030 Challenge has 4 distinct guidelines. First is to establish energy efficiency as a central tenet of your firm's design philosophy. Require that all employees become educated in the design of energy efficient buildings. Engage clients in discussions relating to energy efficiency. And finally, approach every project with an energy focus and review the project for further energy reductions at every stage of development. So if we look at statistics here, this is taken from the U.S. energy consumption and 2030 challenge. Basically, buildings consume about 40 to 50% of the total energy in the world. Approximately 75% of energy consumed by buildings is electrical energy. So how can Autodesk software help us meet those challenges? The first thing we need to look at is where is the most work can be done to impact the most, give the most results. And what we found out is that that design strategies at the early concept design of the project impact the project the most and produces the most effect. And the largest energy reduction can be achieved through design. So this is why this webinar is focused on sustainable design and simulation in design. Here are 3 resources for you to do some further research on your own: architecture2030.org, AIA.org, 2030 commitment, and insight360.autodesk.com. For those of you who have not heard of Insight360, it's the cloud service that comes along with Revit 2017 and Format 360 Pro as well. So there are three factors or pillars to this: the stakeholder engagement, whole systems dynamics, and design process continuity. It's obvious after all of this discussion is that the energy simulation is the key to meeting the 2030 challenge, because how otherwise you'll be able to validate objectively that you meet those challenges. You need something that is dynamic, that is continuous, and then involves all stakeholders, and it's also easy to use by design professionals. So we've covered this in a previous webinar. We talked about the AEC collection by Autodesk that just came out in August 2016, just a few weeks ago. And Autodesk has added a whole range of apps and cloud services for you that will help you achieve those challenges. Forma 360 Pro, InfraWorks 360, Insight 360, which is embedded inside Format and Revit, and then Recap 360 Pro, as well as structural analysis for Revit. So that covers the whole range of architecture, mechanical, and structural disciplines. So energy analysis for Revit has been around for a while, and it shows up on your menu when you install Revit 2017. And let me run this quick video to describe the process of using an energy analysis for Revit. If you have used it in the past, it has improved a little bit because it now includes both the Green Building Studio engine as well as the massing approach and early concept design, as well as the component approach using the actual Revit components and system families and such as floors, walls, and roofs. So within the Revit application, you're creating these energy masses that shows the zones of energy based on different percent glazing and rooms and spaces, and uploading that energy model to the Autodesk cloud and getting feedback on how the building will perform under certain conditions. So you can set certain parameters, and then when the results come back, you'll be able to view them side by side and compare design options for energy performance. So this has been around for a while, and it forms the basis of energy simulation inside the BIM authoring tool. So today we'll be looking at other tools as well. So here we're showing how you'll be able to set the geolocation of the project and even select the weather station that's applicable or nearest to your project. Again, this is based on Green Building Studio, but it's focused on energy itself. Here's the version of the energy analysis that deals with monthly cooling loads, fuel consumption, electrical consumption, and peak demand. And then it shows also the wind diagram. So along with that, of course, comes cost information that can be that you can improve your decision-making process and compare the cost impact of these energy runs. So next, of course, is Green Building Studio, which we covered in a previous webinar. I'm just going to touch on the highlights and move on to other applications. Green Building Studio deals with whole building energy analysis with detailed weather data, Energy Star and LEED support, carbon emissions reporting and daylighting, as well as water usage, cost, natural ventilation, and potential. So this forms the basis of your BIM authoring tool that links to cloud analysis. Now with Revit 2017 and Format 360 Pro, you get Insight 360. Insight 360 is the cloud service for Revit and Format. allows you to create fast, intuitive analysis for three things: solar, lighting, and energy. This is pretty advanced because that meets the requirements set forth by the AIA 2030 challenge, and allows you to use very user-friendly tools to determine, photovoltaic performance on the building, cooling loads, heating loads, comparing different options, and shows you a color-coded version of your building based on what part of the building receives the maximum solar energy and where to place your shading devices. Back in Revit, you can show on every level of the building the lighting analysis, and gives you feedback right there in your BIM authoring tool on how the performance of the building is maintained. Very, very, very advanced tool, and it deals with the building life cycle analysis in addition to all what we are used to in the past as the solar and the energy analysis. So now comes the part of the simulation. So how does simulation plays a role in building design? We know that simulation has been used for years in manufacturing. So how does that, how is that applied to building design? First, the question is, why simulate? Obviously, the answer would be to validate and optimize design, to reduce reliance on physical testing and mock-ups, and then accelerate design development. It's pretty costly to create a wind tunnel, for a building. So the building is gigantic. Now, the first thing that keep in mind is that this is not just about energy. It could be also about other things that move around in around the building, such as traffic, vehicle traffic, and pedestrian traffic. So using InfraWorks 360, we'll be able to study the traffic patterns, pedestrians in a multimodal fashion. So let's take a look at that. So InfraWorks 360, using mobility simulation, allows us to study different modes of transportation, such as buses, trains, pedestrians, cars, even cyclists, and how they interact with each other in a specific urban area. So you can just specify a certain urban area that you want to study for your project. And by changing the infrastructure of the site, design roads, bridges, roundabouts, you can trigger a simulation that by defining certain constraints, just simple constraints about how many cars are running, at what is the peak demand, what is the hours of operation, and cars are going to stop at the stop sign, and they're going to turn, observing the traffic rules, and wait for each other. And by doing that, you'll be able to predict the performance of your infrastructure in advance. So that's one way to work with simulation. The other one would be for pedestrians. For example, in this terminal, airport terminal or seaport terminal, people waiting in line and designing for peak demand. When you have multiple modes of transportation, cars, buses, people, cyclists, all come in the same place in a busy downtown area like that, the issue becomes complicated, and it's just not possible to do this manually. You have to rely on the computer to simulate that for you. So InfraWorks 360 does a great job at that. Let's look at simulation CFD. So CFD stands for Computational Fluid Dynamics. That is the abbreviation for the many applications that uses the technology. So it's always been a situation where people dealing with force of water, force of wind, and simulating the flow of these fluids. But that just takes a lot of scientific background. and requires people with a very high level of scientific education to be able to run this type of application. The software revolution that Autodesk brings to the table will allow us to predict the flow of fluids, namely water and gases, and around the buildings, as well as other machines. So CFD, computational fluid dynamics, presents an user-friendly analysis application that by using cloud services, you'll be able to predict the performance of air and water and even thermal heat gain and loss in a building using the software. So this will eventually reduce the risk associated with that performance. If you have a hurricane or tornado in a zone, then you want to know in advance so you can design for that. When it comes to machines, different stresses and performance also will determine how that machine will perform. That can be studied on a large scale or on a small scale, as depending on the need. So fluid flow is the study of gases and liquids, how they flow through objects. Heat transfer is another aspect of it. The software is able to color code the object or the room for that type of load. Even people sitting in a meeting hall require a certain level of comfort. So basically, the way this works is that you have a space with intake and supply and return air, and you're stimulating the flow of the air in the room, and you work that based on occupants. The design will evolve based on the distribution of the supply air and return air outlets or diffusers. In the case of the hospital, surgery rooms, the contaminants in surgery rooms should not be cycled around and moved to other rooms. So they would have to be eliminated from the room as soon as possible. So that's what simulation CFD does. All right, so what are some of the challenges for CFD? The image on the right kind of shows in a nutshell what's going on here. So you have the person on the left is receiving cold air from the diffuser above. He's very cold in the summertime, and he's going to be very hot in the wintertime. The guy in the middle is okay as far as comfort level, and the person all the way on the right is going to be very hot or very cold because he's too far away from the supply air. The distribution of the HVAC system diffusers is critical. You don't want to wait until the building is completed and construction is over before you test that. You want to do this as soon as possible to get the maximum impact. So some of the questions you ask yourself is how to achieve the balanced airflow. What is the temperature variation? Will the occupants be comfortable? How will temperature variation affect equipment? And will the room be too hot or too cold? Should we add a sun shading device to help the HVAC system from a sustainable standpoint? And is ventilation optimized for running costs? And how can we heat or cool the room more efficiently? All right, so there's a couple of applications that are have been used for a couple of case studies. This case study has to do with a partition between two different compartments in an airplane. So Airbus 2050 is designing a futuristic airplane that requires a light. They want the components inside the plane to be as lightweight as possible. So Autodesk used generative design to design that, and then they also used simulation mechanical to understand what kind of stresses are imposed on that partition. So for that they used Fusion 360 to design the partition, and then use simulation mechanical to run the analysis. Let's take a look at building structure analysis, and that's for wind simulation as well as deflection and pressure maps. So you can run it within the application. You can run simulation CFD within robot structure analysis, or on its own. So robot structure analysis allows you to set the direction of the wind, set the wind velocity and wind pressure, and simply when you finish with all the different parameters, we'll show you the wind profile, and then you can simply just start the simulation. That will generate the meshing, the simulation, the load generation, and start creating these color-coded pressure maps on the building that will help the structural engineer in determining what part of the building needs special reinforcement or special attention.
The results of this simulation can be used for further analysis to verify a typical approach.
So the results can be used to study the shear and the bending moment on different structural elements and achieve optimal design without over-designing. Okay, so some of the business challenges associated with the simulation are project over budgets. That's kind of typical. Schedule uncertainty, customer unsatisfaction, high risk margin, fierce competition, increased global competition, increased project complexity, regulations, sustainable requirements, stakeholder engagements, and you're limited by hardware for the most part, because this is hardware intense. And then CFD requires typically scientists with PhD level genius, essentially. So how do you solve these challenges? Basically, you do virtual testing, and that eliminates a lot of the unnecessary costs associated with physical testing. You can remove the uncertainty from a project timeline, and by improving the quality and customer satisfaction, reducing unknown risks, secure competitive differentiation, win global business, predict building performance, and comply with regulations and exceed sustainability requirements by optimizing the design. And you can visualize the design in any dimension, 2D, 3D, 4D, 5D, if you want. And this is cloud enabled with infinite computing power, so you don't need to rely on the local hardware, and just leverage the power of the cloud, infinite computing for that. And then of course it's democratized for anyone to use. It's not solely dedicated only for PhD level people. So anyone can use this because it's so friendly. All right, so I'm going to be talking about the case study, and this case study is going to leverage the highest level of sustainable design possible. So above and beyond the green building challenge, the LEED requirements, there is something called Living Building Challenge 3.0. This is made by the International Living Future Institute, and this defines the most advanced measure of sustainability in the built environment possible today. There are 7 performance categories called petals. They are place, water, energy, health, and happiness, and materials, equity, and beauty. Now this is kind of challenging because how do you define beauty? I think if you were to watch the next few slides, it will talk about the case study and how one of the uh, Autodesk, I guess, customers was able to take this challenge and leveraging different techniques was able to achieve a higher level of sustainability. Net zero energy building certification is also was also used on this case study, and this requires two things: verifying that net zero energy building performance exists in the building, and this requires a 12-month documentation period. So after the building has been built, you would have to document the building performance in order to meet those high standards. The case study has to do with DPR construction. DPR is a national construction firm based in California. They have decided to open an office in Phoenix, Arizona, and they just have taken over they bought a building that was abandoned in a kind of a not so neat area, and they wanted to basically establish a downtown presence for them that can improve the urban network in downtown Phoenix. So they've decided to implement the highest level sustainable design possible in the building. They use many different techniques, from vegetation to water dripping to solar lights, etc., to achieve those guidelines. Now, Phoenix is a very hot area. In the summertime, average temperature is about 100 degrees Fahrenheit. So you can imagine how much effort it takes to achieve that. So they've relied on these guidelines for the Living Building Challenge, and you can see where the Living Building Challenge starts to happen. It's all the different green building codes reside down here, and this kind of gives you the negative environmental impact. At the point where the green building codes or your project achieve a zero environmental impact, which is carbon neutral design, you're starting to work with the Living Building Challenge. So this is extremely positive and gives you positive environmental impact. So it's extremely hard to achieve, but apparently DPR Construction was able to achieve a lot of that in their Phoenix headquarters. So let's take a look at some of the examples. Of course, it has to do with simulation. This is our topic today. So simulation they used was based on CFD. And they had these solar chimneys that sucks the air into the building from different openings and then lets the air out through the roof of the building. So they use solar chimneys, solar tubes, passive cooling tower. So this passive cooling tower drips the water on the outside of the building, and that runs a water screen in front of the ventilating windows with louvers, and then the air is sucked into the space through different natural processes, including ceiling fans, and then it's channeled throughout the space, cooling all the occupants, and then is naturally just rises up and exits from the solar chimney. The solar tubes will provide natural light for the interior of the building. DPR also have a dashboard, a building dashboard. It's almost like a live dashboard that shows the solar production and total consumption of energy within the building at any time. So they can, they can monitor this once in a while, and then, especially during the peak hours, and they can start, given certain sensors in the building, they're able to open and close different louvers and let the air in and out, even when there are no occupants there, all depending on sensors, temperature sensors, and light sensors. That's going to optimize the project energy consumption and saves a lot of money, of course. So on the roof plan, you can see that they use the solar thermal panels, thermal chimneys, mechanical units, tubular lighting devices, and shower towers. And all the combination of all of these techniques achieve the maximum return on energy. So Autodesk has been busy producing a lot of different simulation applications, and they fall under the simulation products. And I've selected 4 of them that are significant to building design as of today. They are simulation and CFD, flow design, robot structural analysis, and simulation mechanical. These are the most significant ones. Okay, so let's take a look. So the first thing I want to talk about is temperature control. Temperature control is has to do with how the occupants of a certain space feel inside the space. Here's a case study that was actually done a few years back that shows 2 occupants in a lobby of an office building. One person is standing on the mezzanine level above, and one person is sitting down on the chair in the lobby. So the design team wanted to know how the occupants felt during winter months or summer months in this space. They've used simulation CFD for that. They've created ISO surfaces, which shows clouds of continuous flow. These bubbles you see on the screen, the yellow bubbles, and the blue bubbles, are clouds of continuous flow of either hot air or cool air. Of course, the hot air is the yellow colored air, and the blue is the cool air. You can tell by looking at this that the occupant, the person sitting in the lobby, is not comfortable. If you look at the legend, he's getting air in the range of the mid 60s. So mid 60s may not be a comfortable temperature in winter time. You need to bump it up to the 70s for that person to be a little bit more comfortable. The person above feels just fine. So the architect had to introduce radiant panels below the mezzanine level so that the occupants below are able to feel comfortable during the winter months. So they used the predicted mean vote for humidity, temperature, amount of clothing that the person is wearing, and getting the feedback from the occupants. With different distribution of the diffusers and radiant heat, they were able to achieve that comfort level. So, of course, the comfort level is important in transportation, in buildings that have atriums with multiple levels, and of course assembly halls and theaters where it's just hard for the air to be directed towards a specific occupant. Of course, it becomes very critical when it comes to hospitals and other critical facilities where you have to do something about it. In a hospital room where there are contaminants in the room during the operation, you want to pull this air away from the patient and push it outside as soon as possible. So the CFM number has to increase quite a bit for that. Also, simulation can be for natural ventilation, typically by creating courtyards. Some of the buildings here, I think, are in China, that allow for the air to just keep flowing and then reduce the load on HVAC systems. Smoke migration is another aspect of this. It has to do with closed garages and the parking decks, where if there's a car on fire, how the smoke will travel is predicted in advance so that to save lives. Wind simulation is going to be a major aspect of this because in an urban area such as big cities in Los Angeles, New York, Atlanta, Miami, and other cities around the world, when you have such a dense layout of buildings, the airflow can either speed up or slow down depending on the configuration of the buildings themselves. In data centers, cooling and heating, just changing mixing the air that's shown on the right-hand side, mixing the air coming out of the data center room with the intake air will help reduce the load on the AC system and therefore produce a more uniform cooling ability to the data center. Supply chain buildings, HVAC, simulation can help in determining the floor coverage as well as make sure that the goods that needs to be delivered to their destination remain fresh and healthy until they get to their destination. All right, so let's take a look at this simulation. We all know that well-designed buildings should be structurally sound, but also the comfort of pedestrians is very important because it has to do with how the air flow around the building. So when you have a channel that enhances the wind speed, this could cause either comfort or discomfort for the pedestrians. There also can be hazards caused by moving air. So this includes dangerous gusts that forms between buildings, strong downdrafts on the leeward side of structures, and still air that can keep the pollutants in the same location, and that causes a health hazard. So when you work with applications such as flow design, you'll be able to set the wind speed and the wind direction, and then get a closer look at how the building design will perform and become more supportive for the life inside the building and outside the building. Okay, another case study here for is the Century Link Stadium in Seattle. So this is a wind simulation for a sports facility. Let's take a look. So Autodesk was helped the design team on this project to perform a wind simulation. So basically they load the project model using different file formats, including STL, which is also used for 3D printing. As soon as you load it, the simulation starts automatically, and basically you're just going to set a different shaded graphic display options. So the air now moving from left to right, or now from right to left, is going through that pillar on one side of the stadium, and by focusing our attention on a specific part of the stadium, we'll be able to see the flow lines of the simulation. And what that's doing is creating a vortex of wind inside the stadium. That vortex behavior can have a big impact on sports people like kicker or a quarterback, and you can get the ball in the right location when it's so intense. So the design is going to help the occupants of this stadium not only feel more comfortable but also perform as they're supposed to perform. When it comes to orientation, you can just flip it around, and this would be similar to the physical wind tunnels, where you actually put this model on a turntable, spin it around, and then simply run the simulation through the building. So this is virtual simulation, reduces a lot of time, and it doesn't cost that much to do it. So if you run the wind from the other side of the stadium, you see that you may get a different result.
Again, we do have a concentration of pass-through airflow on one side of the field. This time it's on the western side of the field. So despite the extra stands and the sign poles, and that's the language that you make should reduce extra blockage, looks like that.
So studying the design from different angles will help the AE professional determine the optimum orientation of the building on the site, and therefore getting the best result. So this is basically just a quick study and just part of the design process. Another example of wind simulation, and this is for a residential building, that I did created some time ago with Autodesk Falcon. This was a lab product some time ago that was the beginning of making the simulation friendly for users. So basically, just designed this building in Revit, took it to 3ds Max, brought it back into Autodesk Falcon. I was able to simulate the wind impact on the building, and you can see here by the legend that the yellow areas on the building are have the most impact from the wind. And in case of a tornado or hurricane speed wind, this could produce an uplift on those areas, so that the soffit of the roof can just peel off and then fly away. Also, just like you would do a simulation for the stadium, even on a small building, you still have this air that's going to just cycle around and come back. And all right, so let's move on to something else. So this is a hospital building that has some symmetry in it, and I thought it would be interesting to take a look at the wind simulation for a hospital building. So I've pre-recorded some of these videos so that we don't have to sit there and wait for it to perform or to produce results. So you can see that symmetry of the building produces symmetry in how the wind will behave. Interestingly, that's going to be very useful for the designer to be able to make those design decisions for both views, ventilation, solar performance, energy performance, as well as wind performance. So there's different representations of the wind simulation, including velocity and pressure, and some of the useful simulation for this building was when I started looking at different wind directions and understanding that the blue lines means either very slow wind or actually could cause negative pressure on the building. Now, using different representations, including flow lines and 2D and 3D modeling capabilities, achieving different results. Again, this is a quick simulation. It doesn't take that much time. It's could be run with your native modeling tool, and either on the cloud or on your desktop. Okay, so the last simulation I want to run here for this has to do with isosurfaces. So as you can see, isosurfaces produce this monster, green monster, I call it, that if you look at the legend, you see that the green monster indicates negative pressure on the building. So this is a continuous negative pressure on the building, which means that this part of the building that's covered with this green bubble will probably fly away in case of an intense wind. So the architect and structural engineer would need to design for this type of negative pressure. When the pressure becomes blue in color, it means that you got some severe negative pressure. On the other hand, anything that's in orange is very high positive pressure on the building. Here's the blue negative pressure. Okay, I'm actually going to move on here to something else. This is a React structures. That's a new structural analysis software by Autodesk that allows for the study of finite element analysis as well as wind pressure. And I'm simply just going to move it forward to show you the wind analysis simulation.
Wind load simulation feature enables you to simulate a wind flow around your structure and generate wind load.
So almost every Autodesk software right now is concerned with how the building will perform, all the way from Revit to Format to React structures and flow design. So when it comes to buildings that have complicated geometry, it's hard to predict this performance unless you have the software help you in this prediction. All right, so this building belongs to this case study, and this case study is the U.S. Air Force Academy in Colorado. So Autodesk for this particular project, they used Revit, of course, the hub of all activity, Autodesk Recap, energy analysis for Revit, lighting analysis for Revit, simulation CFD, and robot structure analysis. All the different applications were used together to produce these results. So Recap was used for laser scanning and to scan the existing building. Revit, of course, was used to model the as-built BIM model, and it was used for in other applications for energy analysis, lighting analysis, and computation fluid dynamics, as well as structure analysis. Here you can see the Autodesk CFD that was used for to simulate the movement of air inside this chapel. Right. Another example of simulation is the Walkie-Talkie building in London. It's a London high-rise building that looks like a curved skyscraper. It's the one on the far left of the screen. Somebody sued the building owners because apparently the curvature of the building produced such a sharp concentration of sun energy on one spot and on the street. There was a Jaguar car parked there, and half the car was part of the car was melted due to that. So Autodesk and NVIDIA used the I-ray measuring tools to simulate the reflected light from the building on the street, and it turns out to be about 170 degrees Fahrenheit. So that was pretty hot. I've also used flow design myself to bring in some wind turbines. This was part of the Georgia Tech building I was helped work on in the past as a consultant. So these wind turbines were on the top of the building, and it was able to take those wind turbines and simulate how the wind will flow in around those turbines. And apparently, when you have such a symmetrical pattern in those devices, you also get a symmetrical pattern in how the wind will flow. And I thought this was interesting. So it's very colorful, very attractive, but also it helps you understand the spacing of these turbines and how they relate to the environment around them, and so you don't have to impact what's around. I use the same application, flow design, to study the impact of wind on a high-rise building in the city of New York. So the tallest building in the middle is the one that was was created as a mass. And even early in the design process, on day one of design, you'll be able to generate those masses and run the wind and see the impact on the building itself. And anything that's in yellow, of course, is high-speed wind. Anything that's blue is negative pressure. Okay, last but not least, and I'm going to turn it over to Casey in a minute or two. I would refer you to this YouTube video. This is a Stefan Belling. He's an architect who practices in London, and he describes high-rise buildings as submarines that prevents people from seeing, from smelling the fresh air outside the building. So they're too close to the glass, but they can't smell the fresh air. So what I'm going to do is I'm going to fast forward, since we don't have a lot of time, to some of the highlights of this. The first highlight would be around here, where he describes the varying sensory stimulation as something that's required by the human brain. So if you just provide the perfect environment for the human, it will still need some excitement and some change. So that's why people get bored from high-rise buildings and closed offices. The other thing that he describes as is the quality of light. So the quality of light in the morning is not the same as the evening. In the evening, you get melatonin is produced in the body and helps you to go to sleep. So if you're in blue light all the time, you can go to sleep. So that's important also for the human psyche. Then he describes that in order for people to be psychologically pleased with their environment and their work environment, they need to see the rain, smell the trees, etc., the grass, and by putting people in closed boxes, that doesn't help very much. So HVAC is not really an ideal way to cool or heat the space. So bringing the outdoors in is important. The other aspect of this has to do with going to space now at a different level. Astronauts tell us that the things they miss most about being in space is the smell of fresh air after family and friends. So so they've created, NASA created this window that is applied to these space ships that allows people to see outside and interact with what's around them. The other thing has to do with here's the guy. This is Stephen. So this is the window that was designed by NASA, was engineered out of the project and then was put back in. So let me run this. Basically, he talks about him being hired as a consultant for a number of things for projects on Earth and on Mars. He talks about the habitats on Mars and how they were, planning to send small robots to collect things. But the focus here is on people's comfort. How will people feel inside the building, and what kind of texture, light, quality, plants they need. It's not, they don't want to live in plastic boxes. They want to live in environments similar to the ones they live on Earth. So his practice has turned from just architectural services only to something that includes scientists. So his practice includes scientists such as this one, and they were trying to measure the level of excitement for a person walking around in a built environment. So this could be inside the building or outside the building. This simulation simulates the emotional mapping of a person walking around the city of London. So he's also talking about simulation of the comfort of level of people. Do you do a physical model of the inhabitants, or you do it virtually. Of course, virtually is easier. He also talks about when he was hired to be the consultant for the Apple campus in Cupertino, California. The issue that came out working with Steve Jobs is what is the perfect environment that encourage creativity and nurture innovation. So the idea, they wanted to break down the barriers between the inside and out and created the largest sheet of glass and then bring some of the air in through these vents. And this is a simulation I was showing how the air is coming in. And so people can smell the fresh air and the trees and the flowers and the seasons. And people walk in the park, run in the park, and then, you know, it just became more user-friendly. The last thing that he talks about is the Big Apple flagship building in Union Square, San Francisco, where he let the evening breeze in through the windows. And when Apple has a meeting for a crowd, they just open these huge doors and just let people in and out, interact with each other. So this is what simulation produces quality spaces for the inhabitants.